Okay, we'll get started then. And so, how's the homework going? Good. Okay, it shouldn't be too terrible. I know some of you guys are experiencing some problems with the image magic thing. Did you guys get my invitation to Piazza also? Yeah. Yes? Okay. All right, so if you have not signed up for that, I think last quarter I used it in my classes and the students found it very helpful. So, I mean, it's not a required thing. But on Piazza, I found, I posted this link to Cactus Lab. So this is for people with Macs. If you're having trouble getting image magic to work, I found this thing. I don't have a Mac, so I haven't tried it out, so I can't say that it does or does not work. I had the online thing run a virus scan, and it says it's fine. So, I mean, it seems legit. Has anyone tried this one? No? Have anyone with a Mac got their image magic to work to export a GIF or GIF?
I downloaded it, but when I ran my function, like
same error. So you installed this and it still didn't work?
Yeah, it's like it still needs some more stuff.
Okay, all right. We're going to have to... well, if anyone figures it out for the Mac, please definitely share your experience and tips with the class, just because I don't want the image magic thing to be the stumbling block in the experience, okay? But a lot of times these small technical things on the side end up being the... oh dear, my thing is going...
Is there any other way of...
Something is... My computer's going crazy here. Stop. Okay. All right. Yes.
Is there any other way of making the GIF without image magic?
Not with that package animation. The package animation is designed to work with image magic. So there might be a different animation package that I am not familiar with that might be able to do something similar, but I don't know. Okay. Now, image magic does, not image magic, the animation package does support other exports, like you can export to PDF, which actually supports animation, and as HTML. But I think kind of the standard way to view animations on the web these days is through, is it GIF or GIF? See, is this a divisive issue? Okay, well, I don't know. So, well, you say GIF? Okay, I'm saying GIF, but maybe it's GIF. Who knows? Yeah. I'm sure there's I think I saw some satirical thing about, yeah, whatever. Okay. All right. So we are now going to start talking about principal component analysis. Your TA should have been introducing kind of concepts behind eigenvalues and eigenvectors and PCA and stuff. How are we feeling about kind of this matrix algebra stuff? Bad? Eigenvalues, how do we feel about that? Bad? Oh, man. Okay. All right. Okay. Well, all right. Well, then maybe this will be good. I came across this thing. I was just trying to search for useful ways to explain eigenvectors and eigenvalues. I know as a student, I struggled very much with this concept of eigenvectors and eigenvalues myself. I kind of have an understanding now, but I know it was difficult for me when I was learning. So, just because I think the thing that we always see being presented is just something where it's like, AX equals lambda x, and it's like, well, this doesn't seem very useful. And then they say this is a vector, and this is not a vector. This is a matrix. and this is a scalar, right? And you're like, okay, you know, and this means, you know, this is the eigenvalue. Gosh, my handwriting is terrible today. And then the x here would be an eigenvector. Okay, you know, I'm so embarrassed by my handwriting here. Let me just rewrite this, please. Okay, so we have ax is equal to lambda x, okay, where A is a matrix, okay, x is a vector, and over here we get a scalar, and this is still the same vector, okay? And if this is the case, if we can do this, this is called an eigenvalue, and this is called an eigenvector. Okay, now why would we care to do this? Or, you know, what does this even mean? And I found this, this is like, I thought, just a very good and clear explanation. But of course, you know, what's clear to me may not be clear to you. So I'll do my best to try to explain what this explanation is, and I'll be sure to link to the page on CCLE, so if you want to review it in your own time, you can. And then, okay, so then I feel like, you know, once we kind of get this down, we can start talking about principal component analysis. Okay, so basically, okay, so I used x, but this page used v. Okay, so I hope that's not too confusing. So you can think of v, you know, a vector that, you know, it's just kind of like 2 points here, all right? You know, a coordinate thing, okay? And then, and A is a matrix, okay? And so we can think of, can you guys see this? Maybe I'll zoom in. You can think of matrices, you can think of them as several ways, but here we are thinking of matrix as kind of a set of operations that transform a vector or a point, okay? So basically, our A here is we're taking kind of the, here it says A1 is going to be 1 in the x direction and 0.5 in the y direction. And over here, A2 is 0.5 in the x direction and 1 in the y direction. And basically, we apply this transformation to V, okay? So with, we take our piece V, which is currently at the point 2, 3, okay? And then, you know, we're multiplying A times V. And so this will transform the values of V into 3.5 and 4, okay? And so the result of applying this matrix A, the matrix A, which consists of kind of these two vectors here, result in V ending up over here. So A times V causes the point to move out over here, okay? And so, you know, and this is like a cool little interactive thing where you can kind of move V around and see how, you know, applying A to V changes, okay? All right, so what does this mean? Okay, well, if the resulting thing between I'm sorry, between V and AV, if this kind of the line that shows the transformation between V and AV ends up running through the origin, then we have an eigenvalue, eigenvector situation, okay? Because V is a point, and what basically this, when you have it running through the origin, what we're saying basically is that to get from V to AV, you don't even need to apply the matrix itself. You can just kind of say, hey, scale along the same line, because V by itself, right, if we just multiplied V by a scalar, it's going to go along this line, okay? And that's what this diagram says, okay? If V is along, if V is right here, then we can just multiply by a scalar, and we can end up potentially at where AV is, okay? And so when you have eigenvalues and eigenvectors, basically what we're saying is that you don't need, to go from V to the point A times V, okay? Normally you have, you're applying the matrix to kind of apply the transition, but what it's saying is that if it lies on a straight line through the origin, then what happens is that this entire matrix can just be replaced with the scalar, okay? And that's what we've got, okay? So the matrix, applying a matrix to a vector generally applies some kind of transformation to the value of the vector, okay? And what we're saying here is that, hey, you know what? We can get rid of kind of the, quote, complicatedness of a matrix and just say, I get the same result by just multiplying it by a simple scalar, okay? And so that's kind of the big picture behind an eigenvector and eigenvalue, okay? And I think, and I love this page because I remember going through the same thought process, which was like, oh, okay, well, that's great. Why would I ever want this thing? And that's the exact next question that it says, okay? And basically what it's saying is that when you have a matrix, okay, that applies some kind of transformation, and so in this case, the transformation is apply A1 to A2, and you apply it to some other thing, it's going to cause that other thing to tend towards the eigen, kind of the Eigen Space. So I'm sorry, so maybe I have to back up. An Eigen Space is basically this purple line where V and AV lines up, because once you have an eigenvalue of a matrix, okay, moving anywhere up and down this thing would all be just scalars. And so this entire line here is known as an eigenspace, because you can potentially get any value that shows up along this purple line, okay? And so what we have here is that, if you keep multiplying the some point V to by the matrix A, okay, we get this sequence, V, A squared times V, A cubed times V, et cetera, okay? And what our eigenspace kind of tells you is that, what is the trajectory of this thing, okay? So in our case, we start off at V, and every time we're multiplying by A times V, we end up towards ending up along this trajectory here, okay? And so, if we start right along here, okay, we're essentially just multiplying by a series of scalars, but this is kind of, even if we're not along the eigenspace, continually multiplying by A, or A, or I guess exponents of A causes the points to tend here. So here was an interesting result was with the Fibonacci sequence, okay? And so that says that, suppose you start off with some amoebas in a petri dish, and it says at every minute, all adult amoebas will produce one child, okay? And then all children will grow up into adults. And then this is just kind of the ticking along, okay? And this is not how amoebas actually work, but in this case, okay, so at time t, you've got this many adults, and then in the following minute, the number of adults that you have now is going to be the number of children that gets produced in the next generation, okay? And then the number of adults and children that you have now will be the number of adults in the next generation, because in the next generation they've all grown up, and then they're all having children, okay? And so to transform V into the next generation, we can apply A, the kind of our transition matrix, which says, okay, take your adults and children at time t, okay, and then add those two together to get adults at t plus 1, so you have a 1 and 1 up there, and then adults and children at time t, the number of children in the next generation will just be the number of adults, this one down here, okay? And then the number of children can't have the kids, okay? And so what we have is, you know, if we start off with one child at time v0, okay, this is our original vector v0, one child, 0 adults, okay? In the next step, we now have 1 adult, okay? And 0 children. And in the next step, we will have that one adult will give birth to a child, so we now have 1 adult and 1 child, okay? And in the next step, we will have that 1 adult and 1 child. That child will have grown up, so we'll have 2 adults, and then that adult in the previous generation has another child, okay? And so, you know, after 3 iterations, we have that, okay? So we see that 1 adult, 2 children equals 3, okay? And so the next step we'll have what? 2 kids and 3 adults, okay? And so that points out right here. And then in the next step we'll have what? We will have 3 children and 5 adults, okay? And then so we can see kind of something interesting happening, okay? As I move further along the generations, so I've got 8 children, 13 adults for a total of 21 people, 13 children and 21 adults, okay? What's happening? Each of the sequence here, V1, V2, V3, V4, V, all of these, you know, our sequence of results are starting to line up right along this gray line, okay? And that gray line is the Eigen Space of our matrix A, okay? So anything that lies along here would be considered an eigenvalue of our matrix A, meaning, you know, to go from one generation to the next generation, okay, we actually don't need to know I mean, this is very simple, but we don't need to know the mechanics inside the matrix itself, but we can just say, hey, we're just scaling up along the thing. And then, I don't know, this is just kind of a funny little diagram of its population, which was neat, okay? And then, so we have stuff like that, okay? This is, okay. You can look at the steady states and the complex eigenvalues on your own time. But anyway, I was like, oh, this is so cool. And then lucky for us, they also have one for principal component analysis, which is completely amazing. So I'll make sure to link to both of these, just because sometimes a visual explanation is just is really great. Okay, all right, and so with that in mind, when we talk about principal component analysis, kind of a big use of it is this dimension reduction idea. Okay, so you can think of having a bunch of multivariate data, okay, and you know, whatever, you might have like 6 dimensions, 7 dimensions, okay, and you want to be able to identify countries that might be unusual in you know, the gapminder data, or you know, maybe you need to do some kind of classification or whatever it might be, okay? And here's where did my pen go? So I guess before I get into this page, so let's talk about okay. You know, if we look at just one dimension at a time, we're probably not going to detect very many patterns, okay? And, you know, our brain is much better at kind of detecting patterns kind of as a whole, looking at, you know, the big picture together. But looking at one dimension at a time, we might not see something, okay? And so, I don't know, this is a silly example, but let's say we wanted to look at people versus primates, okay? Okay. And if we looked at just one aspect, something like weight, okay? And, you know, maybe this is like, I don't know, chimpanzees or something, I don't know. And you look at the distribution of weights for humans, and you look at the distribution of weights for primates, there's a lot of overlap, okay? And so you might get some kind of distribution in the data that looks like this. And you can't, you know, and this would be kind of a mixture, okay? So this is people and primates kind of mixed together, okay? So if we pooled all of their weight values in here, okay, maybe, okay, so okay, there, you know, there's no way to really separate them, okay? It's not really possible to separate primates from people based on weight alone. Okay? And if we looked at height, some other aspect like height, maybe maybe we'll get something like this, okay? I don't know, all right? Again, it's difficult to separate based on height alone. Okay, but if we graph these together, okay, what we might see is humans kind of forming something like this, and then the primates might be something like this, where generally, or actually I think I have this the opposite. So where, you know, given the same amount of weight, the human will probably be taller, okay? And so with something like this, we might be able to draw some kind of way to distinguish between humans and primates, okay? When we look at them together. And what principal component analysis will do is then it will figure out the dimensions that have the greatest amount of variation, okay? And once we have that, we can then use kind of use that to classify our data, or just you know, give us some insight into the data, okay? And so with so here's you know, we could have something like height and weight or something, and here there's just 5 data points, all right? And, you know, if we looked at the variation of x, we see, you know, it kind of goes from 2 to 8, or, you know, and variation of y goes from maybe about 3 to 7 or something like that, okay? And what principal component analysis does is it says, you know what, I want to try to reduce this, or not even, it's not even trying to reduce, it's just, I want to find the dimension that exhibits the most amount of variation, okay? And so that is this red dimension. The principal component here is this red dimension, and it says, okay, draw kind of this imagine a line going through this, and we're going to just graph the, kind of, in our case, kind of just rotate the graph of our data so it looks like this, okay? And so what we see here is that almost all of the data, the variation in the data is explained now by principal component 1, whatever that represents, okay? And if we were to just completely get rid of principal component 2, we would not be losing a whole bunch of information, okay? Now, you might get, you can move things around and see, we might get something like this, okay? All right, and in this case, we still have the primary principal component being the red dimension, okay? And then in the looking at the kind of the other dimension, we see this point is a major outlier here, okay? And it's quite clear when we look at the data like this, okay? But if it were just in a table, okay? If this data were just in a table, all right, this data point probably would not stand out right off the bat, okay? Because, you're looking at x goes from 2 to 8. This is not an outlier in the x direction, okay? If we look at y goes from about 3 to 9, or 3 to 8. This is also not something out there, okay? But when you look at it, when we graph it, we see, hey, this one stands out, and then it also appears as something that stands out when we do principal component analysis here, okay? All right, and so, yeah, as you move these data points around, all of these things kind of move about, which is pretty nifty. This is some good stuff here. Okay, and this is this fancy thing, right? Okay, so here we have a three-dimensional data being plotted. Okay, and it's being rotated so you kind of get an idea of what it looks like. Okay, when we do principal component analysis, the first principal component is the component that has the most amount of variation, okay? All of the other principal components after that are all orthogonal, okay, or at right angles to that initial principal component. So you're not gonna have things at angles. You're gonna have them all, they're all right angles, okay? So the first one is the one that has the most variation, and then the next one is, of the other ones that are orthogonal to this, what's the next direction that has the most variation, okay? So basically of the orthogonal vectors to the first thing, okay? So effectively, when it comes to three-dimensional data, imagine this cloud of points, okay? And here it's rotating around for us, but, I don't, can I pause this right here? No, I can't. So, imagine what we're doing is we're trying to find the camera angle that will display the most amount of variation, okay? So what we don't want is we don't want this camera angle, okay? This camera angle makes everything look like it's on the same, that there's hardly any variation. They're all kind of just stacked on top of each other. We don't really see it, okay? What we're trying to do is we're trying to find the camera angle that says, oh, hey, there's quite a bit of variation between there and there, okay? And then, from here, you're trying to find, okay, the next amount of variation, and that's going to be your second principal component, okay? So the original data, looking at x, y, and z, these are kind of the clouds of points. They're all kind of ranging from 0 to 5-ish, something around there. Okay, but we can actually pick out the extreme points according to the principal components by doing something like this, okay? And then if we actually have the computer figure it out, it says these are the principal components that we want to use, okay? Red in this direction, and then the next one is green, which has a little bit more variation, and then the last principal component is the one that is going to display the least amount of variation. Is that okay? Yeah, question.
So the axis PC1
Uh-huh.
is the axis along which the data points stretch the most?
Yes, so it's the axis along which the data points display the most variation.
So suppose my original data points are scattered along y equals to x.
Uh-huh. Yeah.
So if we transform that to principal component analysis, the x-axis becomes the y equals to x thing, right?
Yes, so in this case, the data is kind of scattered along y equal to x or something very similar to that, right?
And is it just pure rotation?
It's so okay. When it comes to if you have three-dimensional data, it ends up being pure rotation. Okay, but as far as and also two-dimensional data, just because the principal components have to be orthogonal to each other, so it ends up just kind of being this rotational thing going on. Okay, but the great power is that you're not limited to 2D and 3D. You can have 50 dimensions or something like that, and then you're rotating the data around. So I can't picture 50 dimensions and knowing what orthogonal things look like in 50 dimensions. But you're essentially doing the same type of thing. You're rotating the data around, trying to find the axes of most variation. Okay, and then the other directions are all orthogonal to that. Okay. One thing to note is that so depending on how your data is recorded, if one of your data has like just huge values, right? You decided to record people's heights in millimeters or something, okay? And then you're recording everything else in just regular units. The height is going to have the most amount of variation, okay? And so that will kind of dominate if we were to do the data directly on the actual data itself. So instead of doing the data directly on the data directly itself, we often will generally create a covariance matrix to capture the variation that exists in the data, all right? And then do principal component analysis upon the covariance matrix. Okay, so here's an example, and this is a 17-dimension example, and here we're just comparing four countries, or I don't know, do they count as countries? If you divide Great Britain into their four lands. Okay, so you've got England, North Ireland, Scotland, and Wales. Okay, so these are the four lands or four countries within the United Kingdom. So I guess Great Britain's just the big island. The United Kingdom of Great Britain and Northern Ireland. And it's like, well, are there any differences? This is how much food they consume. Are there any differences here? And just kind of looking at it, it's hard to see anything, right? Okay. But then you apply principal component analysis to this data, and what happens? It shows, okay, Wales, England, and Scotland kind of together, and then Northern Ireland is all way out here by itself, okay? Now, the unfortunate thing about principal component analysis is that it doesn't, you get a principal component, and you can, from the loadings on the principal component, you can get kind of an idea of how it works, of what's important, but it in of itself will not tell you what is the important data, or what are the important variables, okay? But here we see, okay, Northern Ireland is quite profoundly different from the other three, okay? And so we're looking, you look very carefully, and you say, oh, in Ireland, they eat a lot of potatoes, okay? And they don't eat as much fruit, okay? So all of your stereotypes about Ireland is supported in the data, okay? Well, it's kind of funny, but then it's just like, oh, that's just how the country goes, right? If we threw another country here, right, like an Asian country, it'd probably show, well, rice isn't listed, but I guess cereals. Well, I guess it would just show up really high, right? So anyway, you can graph this. You can look at the first two principal components. So, with 17 dimensions, you can generate up to like 17 principal components. But oftentimes, because just we're used to seeing things in 2 dimensions, you often just graph the 2 primary principal components, and you kind of see this. But it will not, in of itself, tell you just which things are important, okay? So, kind of delving in, with R, we can do some of this. And so I've posted from our textbook, there's kind of like this little investment table on, and let me clear all of this stuff out just because I'm going to run out of time. So when you, in our textbook, we have this on page 11 in the textbook, or page 28 in the PDF. It says, recommended investment allocations by financial management firms at the beginning of 2011. Okay, so I don't know if this data is completely outdated or if it's whatnot, okay? And so these are big banks that maybe people don't like big banks anymore. Well, I don't know if they ever liked them, but especially now they seem to be under a lot of hate. But anyway, Bank of America says, if you want to, the way you should invest is put 53% in U.S. stocks, 9% in foreign stocks, 3% in like developing, developing markets and stuff. Okay, and then you got stuff on bonds, which is like considered a safer thing, and then alternative investments and cash. Okay, and so all these different places have different ways to say, hey, you should investment strategies, right? Okay, so you look at like J.P. Morgan, and they have less in the U.S. stocks, and less in U.S. bonds, but more in alternative investments. Okay, so can we pick out like what's a big deal just by looking at this? It's quite hard. Okay, we can try graphing a bunch of these things, right? And so we can do kind of pairwise plots of our investment data. Okay. Oops. All right, and we get this thing, which it's still really hard to see. It's hard to say much from this, right? You're looking at this and you're like, I just see a bunch of dots. I mean, there's a few things. This guy stands out, right? Everyone else is kind of crowding out over here, and he's hanging out by himself at the punch cooler. We have some of these things that seem a little strange, but it's hard to it's really hard to say anything here. Okay, so there is a well, I'll have to talk about this more clearly, but so I'm going to store the results into PC, and there is a prints components. Okay, and all you do is you just feed it the kind of your data. All right, so in this case I have invest, and so one thing that principal components does that I generally don't do with my data, or requires in your data preparation. Normally I have the kind of the company names or row names as a column here, but principal components will get angry if you do that. Okay, so it only wants values, numbers in your columns. Okay, so when you load the data, one of your columns will be like the name of the company or the name of the bank, and then and another column will be abbreviations, which help out when we do the graphing. So you're going to want to change row names into this. Here, actually, I'll demonstrate, even though we're. So if I were to just load, no, where is my data here? Okay. So if I'm loading invest, okay, it's just a comma separated thing. So it looks like this, all right. You know, if I just ask head of invest, it gives me the abbreviations. I guess not manager. This would be the bank. All right. And so what I want to do is I want to actually change the row names, get rid of these two columns, manager and abbreviation, get rid of those columns so that the only columns in the data are actual values, and then rename the rows to our abbreviations. Okay, so what I'm going to do is just take, say, row names of invest is, we're going to take invest, and we'll take the second column there. Okay, and so now if I look at head of invest, indeed we have that. And then so now I just want to get rid of columns 1 and 2. Okay, and so now now we just have the data in the columns. Okay, and so now I can just do PC is going to be the result of print components of invest. Okay, it's done. And it says, okay, well, what'd you do? So we say, give me the summary of these results. All right, and so here it says, okay, I found component 1, and component 1 says has a standard deviation of about 15. Okay, and it says it explains 65% of the variance. Okay, so you know, our original data has 8 columns, and so you know it's going to create 8 components, and you need all 8 if you want 100 to explain 100% of the variation. But if you just look at 1, you'd get 65% of the variation, and if you just look at the first 2, you get 81% of the variation. Okay, and then after 3, you get 92, 93%. Okay. And then you can see, once you start getting to component 4, 5, 6, 7, and 8, you're not getting that much more in terms of the amount of variation that's being explained. Okay. We can ask PC loadings. Okay. So this is the these are the factor loadings on the principal components. Okay. And so what loadings are. What basically this says is how much so in our original data we have 8 columns, right? 8 variables. How much do those 8 variables factor into this principal component? Okay, so for the first component, component number 1, we're taking about 70. I don't actually know how to. I don't know what this means, but basically, this goes from -1 to +1, and so what this says is that the U.S. stocks, our first column, plays a very important role in the first component, and the alternative investments also plays an important role, but in the opposite direction. Okay, and so you can kind of, based on just one component, you are going to be separating those banks that value U.S. stocks versus those that kind of that don't, and those that place a lot of value on the alternative investments. Okay, and the assignment of the directions is arbitrary here, but that's what it has. So
does this kind of act like a correlation matrix?
It's a loadings matrix, which it's not a correlation matrix. It's kind of a how important is this column in this component, okay? What is this component? How am I calculating the values of this component? This component is based heavily on U.S. stocks and alternative investments, okay? And then for the second component, okay, the second component depends heavily on U.S. stocks again, but now bonds play a much bigger role, okay, and alternative investments. And so it seems like these are kind of the three key things that matter. It's still hard to say exactly, you know, there's not we don't have a name for this component, okay? It's not like, well, I don't know, okay. In some cases we can name them, okay? And, I got like 10 seconds left, okay? And you can create a plot of just your first two principal components. It's called a biplot, okay? And this is what it looks like, okay? And so here we have plotted all 27 of our banks onto the first two principal components, okay? To see, you know, how they differ, and we can see, and the red lines show kind of the factor loadings, okay? So U.S. stocks are quite important for component 1 and also important for component 2, okay? As far as component 1 goes, alternative investments is very important, but in the opposite direction, okay? And everything else is very small, okay? And then, but for component 2, the bonds play a large role, as well as stocks and alternative investments, okay? And so these show you where the things go, and so we can see, oh, okay, so this bank right here, GS, this one differs from the others in kind of their placement of alternative things. So let's, you know, if we looked at that row, yeah, indeed, they've placed a high thing on alternative investments, lower thing on U.S. stocks, okay? So, so you have something like this, and you can kind of see what this does. So HC here, it goes very high in this direction, which means it's probably placed a lot on U.S. bonds, and it's in the middle of the road for alternative and U.S. stocks, so it's probably, you know, middle of the road there. So HC, let's see where they have, okay, yeah, U.S. bonds, 40, okay, and 15 and 25 for the other ones. So those are probably kind of middle of the road numbers for U.S. stocks and alternative investments, but a high number comparatively to everyone else for U.S. bonds, okay? And so this kind of tells you how things differ in these two dimensions that are still unnamed, but kind of we can see kind of are heavily influenced by these three things: U.S. bonds, U.S. stocks, and alternative investments here. Okay, we'll end there. On Friday we'll continue our discussion of PCA.